Hello, today we're going to solve problem 41, chapter 8, Giancoli physics. Let's start off by stating the problem. We have here M1 and M2, which are attached to strings that wraps around a pulley. Now in this particular case, the pulley is not massless and frictionless, but has rotational inertia associated, and that will influence the degree at which this system will accelerate, as opposed to the problems that we solved in chapter 4. So let's assign some vectors to this diagram, and I'm going to show arrows at first, and then I will write in what those arrows specifically represent. So I'm showing the tensions in the strings. Okay, I'm going to show the action-reaction pairs, because in this case these tensions are going to provide the torque for which we're going to use Newton's second laws and rotational equivalent along with Newton's second law for the linear stuff. So here are the vectors that are acting on M1 and the tensions that result, and here are the vectors on M2 and the tension result, and then the action-reaction pairs with respect to the tension and the torque applied to the pulley. Now let's go ahead and write in what these forces are. This is M1G. Okay, let's call this T1. And this is also T1. So when we make our substitution, we're going to use T1 and allow us to merge the two equations together. The linear version of Newton's second law and the angular equivalent of Newton's second law. So as we continue here, we have M2G, and we have T2, and this action-reaction pair. This is also T2. All right. Now, let's start off with our statement of Newton's second law. The sum of the forces equals ma, and we're going to develop expressions for M1 and M2 using Newton's second law. So let's start out with M1. We have T1 up minus M1G down, and that's equal to positive M1A, because I'm showing my diagram that M1 is going to go up while M2 is going to go down. Now, here's the expression for T2, or M2. We have T2 up minus M2G down, and that's going to equal minus M2A, okay, owing to the fact that M2 is going down. So here are these two expressions that we're ultimately going to use to substitute in the rotational equivalent of Newton's second law, and that is the sum of the torques is equal to I alpha. Now, in this particular problem, we have two torques. We have a counterclockwise torque and a clockwise torque. Let's list the torques and then set it equal to the rotational inertia of the wheel multiplied by the angular acceleration of the wheel. So here we go. We have R cross T1, and that's positive because that represents a counterclockwise torque. In our convention, clockwise is negative and counterclockwise is positive. We're going to add to that the clockwise torque, and the clockwise torque is negative. So I'm going to show here a positive, but in parentheses, minus R cross T2. Okay, and then all that stuff equals I alpha. Now I'm going to write I alpha in here, but I'm going to put a minus sign here because the net torque will result in a clockwise rotation. So the negative sign indicates that the angular acceleration is negative. All right, let's go about the business substituting all this stuff in here. And so we have R times T1, and T1 is M1A plus M1G minus R times the quantity. Substitute for T2, we have M2G minus M2A, and that's equal to minus I alpha. Now, I'm going to make a little, we're going to use some simplification here. Now, the rotational inertia I for a disk, let me just write it down here just for reference. The rotational inertia for a disk is 1/2 m r squared. Now, you can find that on page, I believe, 208 in your textbook. So let's substituting 1/2 m r squared for I, And then I'm going to associate alpha with the acceleration, the linear acceleration. And the relationship between alpha and a, I'm going to write it here for reference. Alpha is a over r. So that would be another substitution. This helps us unify both sides of the expression, because on one side we have a linear acceleration, and on the other side we have an angular acceleration. So let's substitute that in as well. Now, the r in question here, since the string is attached at the radius of the disk, we're going to use large r as well. So in the case where, let's say, the tensions were at some other radius, we have to make sure that that's what that represents, as well as the r's that are on the other side. So keeping separate the radius of the rotational inertia continuous body and where the strings are actually pulling or applying the torque to the disk. And they may not necessarily be the same r, but in this case it is. Now, looking at what we have here, we have an opportunity to make some cancellations here. I'm going to cancel the r. There's one of those, and then there's also 2 on the other side, both factors. So we have all the r's go away. Now, let's continue to simplify. I'm just going to clean it up here and rewrite, see, m1a plus m1g minus m2g, and then I'm going to distribute the negative sign through that, so that turns out positive m2a. And that equals minus 1/2 ma. All right. Now, let's collect all the a's on one side and everything else on the other side. So let's see here. I'm going to place m1a plus m2a, and then I'll bring this stuff over to the left-hand side. Makes that positive 1/2 large ma, and that's equal to m2g minus m1g. So getting close now. Factor out an a, and then if you notice, I factor out an a, I'm going to left with a factor of m1 plus m2 plus 1/2 large m. So I'm going to do this in one fell swoop here. So a is equal to the net force, m2g. Okay, sorry about that. So we have m2g minus m1g divided by all the mass elements, m1 plus m2 plus 1/2 large m. Now, in the problem, it does say, compare that to the acceleration of an Atwood's machine without the pulley having some mass associated with it. So we're going to consider it massless, frictionless. So in red, I'm going to give you the acceleration of the system, not taking the rotational inertia of the pulley into account. So here, for comparison reasons, so we have the net force m2g minus m1g divided by the sum of the masses. Now in this case, you're just going to have m1 plus m2. So notice the difference between the acceleration for a pulley with mass, rotational inertia, and a pulley without mass, or a pulley that's massless and frictionless. And you can clearly see that the denominator is going to result in a smaller net acceleration of this system versus a larger acceleration. So there you have it. Have a good evening.